Okay, so I think it's time to start this afternoon session. Welcome everyone. So in this session we have two talks. The first one will be given by Luis Espath. So Luis is an assistant professor in applied mathematics in the School of Mathematical Sciences at the University of Nottingham. His research focuses are on continuum mechanics, numerical analysis, UQ, and physics-informed machine learning. And today he will talk about physics-informed sparse spectral learning. So go ahead, Luis, please.
Hi, everyone. Thank you, Nadir, for the introduction. Thank you, Andrea and Raul, for the organization. So I will turn off my camera. You can see my screen, right?
Yes.
Okay, so my name is Luis, and I will be speaking to you about physics-informed spectral learning. This is a work with Dimitri, Jonas, Puria, and Raul. And the theory and simulations of this work is in this first paper in physics of fluids, and the second paper is going to appear soon, hopefully. And I will start discussing the problem and the type of approximation I will be using. And I will discuss how I use this approximation in the space, the dimension. Then I will discuss two different problems: the discrete divergence free projection and the discrete Hodge-Helmholtz decomposition. So here we let Xi be a mapping from Rn to Rn, denoting a real valued vector field in the dimension D. And this is a physical domain. Then we consider a set of measurements. So these are vector measurements observed at the location Xi. We then seek to perform the divergence-free projection or the Hodge-Helmholtz decomposition of the unknown vector field. And we only have access to few measurements UI, and we have exactly P measurements. So to that end, we construct our approximation on the fractional Sobolev space of all periodic functions that are square integrable on the toroidal D. And here we use multi-index alpha in Zn, but we use a rescale version of this multi-index, which we will call alpha hat. And this is very important to what follows. So we need to bear in mind that the multi-index alpha is a multi-index scale with the domain size in each direction. So here we have n dimensions, right? So with k being greater than 1, we define the L2 and the HK spaces. And the L2, we can simplify for this case because we are working on the toroidal. So we work with the periodic functions that are square integrables. And since these are Fourier coefficient, these are Xi alpha, then by the Parseval's theorem, we get this L2 representation. Similarly, for the fractional Sobolev HK space, we have that Xi belongs to the L2 space, but also the kth gradient also is an element of the L2 space. So it's important to keep in mind that when we have an index alpha here or beta, but a Greek letter, that means that we are discussing the Fourier coefficients. And usually we use just the Greek letter to represent the field. And if we have a calligraph index here, it means that we are working on a subspace of Zn. Okay. So as I said, psi alpha are the Fourier coefficients. We denote here the norm, the HK norm, so the fractional Sobolev norm. So we have the one here just to include the L2 norm, and this will be the L2 norm of the kth gradient. And of course, if we remove this one, then we get the semi-norm. Here, this dot on top of H indicates that we are discussing the semi-norm. However, the L2 inner product may be defined in the classical manner, where we have the inner product between psi and omega as the integral of psi inner product, the complex conjugate of omega, and in a similar fashion for the L2 on the boundary. So here del D represents the boundary of D. And the asterisk is the complex conjugate. So we now are in a position to discuss the divergence-free projection problem. And given a k greater than 1 and epsilon greater than 0 and lambda b greater than 0, we aim to find V opt. So V opt is the argument that minimizes this objective function. So here, the k makes reference to the Sobolev space, to the kth gradient of the Sobolev space. Epsilon makes reference to this parameter that penalizes this term. This is a Tikhonov type of regularization, where we penalize the fractional semi-norm. Then we have the first term here, we have the misfit. V is our approximation evaluated at psi I minus the data ui. And we do that for every point from 1 to p. And we minimize this subject to the divergence of V being equal to 0. Okay, so the second term here that I didn't discuss yet is the penalization of the normal velocity to the boundary of an immersed body B. So basically what we are doing here is we are imposing a no penetration condition to mimic free slip boundary conditions or no penetration boundary conditions. And Vn is computed by this expression. So it's the inner product between the velocity and the normal to the body, to the boundary of the body, immersed body B. The Hodge-Helmholtz decomposition, it's very similar. Instead, given that we have the parameters Kd greater than 1, Kc greater than 1, and epsilon d and epsilon c greater than 0, we aim to find the pair V opt var sigma opt that are the minimum arguments of this functional. And the first term in this functional is the misfit between the sum of these two fields minus the data evaluated at psi I. And we have two regularization terms for the field V and for the field var sigma. Here, these two semi-norms, they don't need to be the same. Here we may choose a different gradient to penalize. But in the numerical simulations, I'm using the same. So we subject this minimization to the divergence of V being equal to 0 and the curl of var sigma being equal to 0. So we want these two fields to be divergence-free and curl-free, respectively. Okay, so it's important here that from the Sobolev embedding theorem, we have that the K that we use here for the semi-norm should be greater than 1 for two-dimensional problems and greater than 1.5 for three-dimensional problems. This is because we need to guarantee the minimum regularity of these two fields. right? Now we are going to see how our construction is made. So for this physics-informed spectral learning type of approximation, we consider a finite series where we have coefficients V alpha multiply basis functions phi. And similarly for the var sigma field, we have coefficients, these coefficients are vector valued coefficients. And we have the same type of basis functions. However, these alpha, they belong to different multi-index sets. So here we have the I multi-index set and the J multi-index set. In the rest of the talk, I will keep the notation I for the divergence-free field and the notation J for the curve-free field. Our basis function are the exponential Fourier basis function. And yeah, we need to bear in mind that these coefficients are elements of the Cn. And from the divergence of this field and from the curve of this field, we arrive at these two linear constraints where we have that alpha hat. And here you should recall that the hat here is because we scale the multi-index with the dimension, with the length of the domain. And here we have, so this inner product should be equal to 0 in order to have a divergence-free field for every alpha in I, and for every alpha in J, we need that the cross product between alpha hat and var sigma alpha should be the null vector as well. So of course, from this condition, we get this condition as well, because alpha and minus alpha are parallel. So we also want to have a field that is real and not complex, because we aim to use these tools in fluid mechanics. So the velocity fields, they are real fields. And to that end, we need to impose the real value representation of V by saying that the coefficients, the Fourier coefficients V alpha, are equal to the complex conjugate V of V minus alpha. And similarly for the coefficients of the curve-free vector field. Okay, so if we gather together the divergence-free constraint with the real value representations constraint, we end up with 8 different conditions, right? So just to clarify here, since V alpha is orthogonal to alpha and var sigma alpha is perpendicular to alpha, then var sigma will be perpendicular to V alpha. Okay, and gathering these two information, we end up with these 8 relations here, but the only one that we care about is this one, where we have that V alpha inner product with var sigma alpha complex conjugate equals 0. Why this is important? Because granted that our field Vi and var sigma J are orthogonal in the L2 sense, and assuming that the boundary term Vi n vanishes, the Hodge-Helmholtz decomposition is unique. We can relax this condition a little bit, but there is no need at this moment. And if we compute the inner product between Vi var sigma J, we know that because of the basis functions are orthogonal, the off-diagonal terms are 0, but the diagonal terms are going to be 0 as well because of this condition. So we end up with the L2 inner product between this divergence-free field and curve-free field being equal to 0. So then it's important to notice now that by construction, we have a field that is divergence-free, another field that is curve-free, and they are orthogonal in the L2 sense. And these three conditions, they hold by construction. So with this, we can guarantee the uniqueness of the Hodge-Helmholtz decomposition. So if we now look at the discrete version of our divergence-free projection, and it's discrete because this field now it's a finite dimensional representation of our Sobolev space, fractional Sobolev space, we may write our functional f to be minimized as the misfit, but now using this sparse construction. And here again, we replace the Vn with a normal velocity given by our approximation, and similarly with the semi-norm, the fractional semi-norm as a regularization parameter. Okay, and then we aim at finding the argument that minimizes f. And here V already belongs to HDiv, and HDiv is given by this additional condition here. And we also incorporate the condition to obtain a real valued field. Okay, similarly for the Hodge-Helmholtz decomposition, we have our functional f now depending upon the pair Vi var sigma j. We replace the infinite dimensional V by this finite dimensional approximation here, Vi var sigma j, and similarly for the regularization of the divergence free field and the curve free field here. And our optimization problem becomes this, where by construction, you know that Vi belongs to HDiv and var sigma j belongs to H curve. And again, HDiv has this condition, and H curve this other condition, and both should be real vector fields. So with this, we finish the definition of our approximation and the definition of the two problems we want to solve. So I'm not going through this whole remark, but I want to make sure we understand what are the consequences of not using a regularization parameter here. And if we rewrite our problem as the argmin of ax minus b, where x here comes from our Fourier construction and b here comes from the semi-norm of our Fourier construction, x opt will be the solution depending upon the parameter epsilon. And if we do a singular value decomposition, and we bear in mind that the right singular vectors are q, then we can say that the x hat is the solution of the same problem, but with perturbation on the location of our measurements and perturbation of the measurement itself. Then we want to bound the perturbation in the solution. So we compute x, our solution without perturbation minus the perturbed solution, and this is bounded by this term, where k epsilon is this kappa epsilon that appears here is basically the norm of A divided the norm of the inverse of B multiplied, divided by the square root of epsilon. So epsilon has to be greater than 0 in order to bound this term. If we use epsilon 0, for instance, we can't bound this term, and for any perturbation, our solution may depart from the true solution. Okay. So I'm not going to show the algorithm, but I want to draw some ideas here to make sure you understand the algorithm without looking at their algorithm. So consider, since we are working with two fields, V and var sigma, I replace this by Xi, because then we make sure this holds for any field. So the energy of our approximation on an index set A is given by the Parseval's theorem, and it looks like this, where we have the inner product between the Fourier coefficients and the complex conjugate of the Fourier coefficients. We define also the energy of the boundary of this index set as the inner product between these same values, but only on the boundary del A. So our algorithm starts basically solving the problem for 9 bases in 2 dimensions. So we assume that we have our index set is given from -1, 1 to 1, 1, and with these 9 bases we compute the 9 vectors psi alpha. Then we measure the energy of the boundary, and this is the boundary. We measure this energy and compare with the energy of the whole index set, and we decide what are, we verify what are the most energetic bases, and we keep the 50% or the 20% most energetic elements of this set. The ones that contribute with less energy we remove from the set, and then we increase the boundary again. We may increase the boundary here, and we solve our optimization problem for this set. And we decide from this boundary what are the basis functions that we will keep. For instance, in this case, we may drop this because they are not as energetic as the other, and then we increase again, and we may end up with this full set of bases. And we do that until the boundary of the energy is irrelevant compared to the energy of the whole set of basis functions. I hope I made clear how the algorithm works. So if you have questions, you may interrupt me. So I will start now discussing some divergence-free problems. And for this problem, we have an underlying field V. Oh, it's a very simple vector field, and we use a residual boundary energy of 50%. That means that every time we increase our index set, we keep only 50% of the most energetic bases. And our stopping criterion is 10 to the -8. This means that when the energy of the boundary represents less than 10 to the -8 of the total energy, then we consider the problem to be converged. And this is for this, so here I used penalization parameter 10 to the -5. This is the parameter that penalizes the semi-norm of V, and with k equal to 1.5. So after 5 iterations, 5 optimizations, so we increase the set of basis functions 5 times, we end up with 43 basis functions. And this is our analytical field, and this is what we get after the reconstruction. Here we have only 10 measurements, are these red dots that you see on the right, and the blue arrows are the velocity measurements. And yeah, after the optimization, we can recover it. These two fields are indistinguishable, and the error is pretty small. So now to assess the error, we define the pointwise error as E of X. And is defined as the true field minus the Fourier construction. And we also define the L2 error, which is basically the integral of this the square and the square root of this integral. And what we will do next is we will compare our Fourier construction with all the radial basis functions approximations available in NumPy. And I'm not going to discuss, but these here in this table, you see all the basis functions defined by default in NumPy. And we studied 10 cases here with 10 different choices. And we studied this vector valued function. So again, here we set similar parameters. The residual boundary energy is 50%, meaning that at every time step, we keep only 50% of the basis. And our stopping criterion is 10 to the minus 7. So the energy has to be on the boundary has to be less than 10 to the minus 7 for the solver to be considered converged. And for the fractional subarray regularization is 10 to the minus 6 with K 1.5. And this after 6 optimization iterations, we get this index set with 53 basis functions. And this is the underlying field. This is the reconstructed field. And they are again identical. So the error is pretty much 0. And we have here 36 measurements. And these are the reconstructions using radial basis functions. And you see that they differ quite a lot from the analytical solution. And this is the error of these 10 approximations. So in our reconstruction, the error is nearly 0. In these reconstructions where we don't have, in places where we don't have data, the error is larger, like in this region and this corner. Here I compare the L infinity error. So our L infinity error is 0.46 and all the others are about 40. And our L2 error is about 0.02 and all the others are about 2. So pretty good approximation we have here. Then this is a third example to assess the quality of the solution. This is the vector field that we want to recover. And the setup is pretty much the same. So here we end up with 89 basis functions given by these blue points. Sorry, I didn't mention, but the red points are the bases that we end up dropping in the end. And this is the analytical field. This is our reconstruction, and this is the error. So here we have 2 regions with almost no data. And our reconstruction is pretty good. As you will see here, in these regions where we don't have data, this reconstruction is pretty bad. As you may see here, we have a big vortex, and this vortex is never captured. And actually this solution is quite unphysical, considering that the field has to be divergence free. So in none of these cases we can reconstruct this vortex here with using classical radial basis function. And our reconstruction is pretty much equal to the solution, to the analytical solution. This is the error of these radial basis functions. Here the same, we have the table comparing the L infinity error and norm of the error. This is our approximation. These are the radial basis functions. So we are way below all these errors. The same for the L2 error here for approximation, and for the Riedel basis functions. This example is just to show that we can deal with immersed boundaries. So here we consider the problem of reconstructing a flow around a cylinder with only one velocity measurement. And the boundary is represented using 100 points. And for this problem, I use a residual boundary of 80%. That means that we keep 80% of the boundary at each iteration. And after 15 iterations, we end up with 73 basis functions, are these blue dots here. And this is the reconstructed field. The blue cylinder is an immersed boundary. Immersed body, sorry, and we have only velocity measurement. Of course, this the information of the boundary contributes to the reconstruction. And this is a three-dimensional Taylor-Green vortex. This is the classical Taylor-Green. And here we need to use a K that is 1.6 to penalize the kth gradient because of the Sobolev embedding theorem. So for all the 2D problems, we use 1.5. For the 3D, we know that it has to be greater than 1.5. And after 3 iterations, we end up with 651 basis functions. And are these basis functions, and are the blue dots correspond to the 600 and something basis functions. This is our set, our index set. And this is the magnitude of the velocity. Here is the Q criterion. This is a quite important criterion in fluid mechanics. And this is the velocity field we reconstruct. So these are 3 different perspectives of our flow reconstruction. And then in the next problem, I want to show basically the L curve. So this problem is the Kelvin-Helmholtz instability. So we have a flow with a stratification in the velocities. We have 2 layers of fluid, where one layer is going right and the other layer is going left. That generates a vortex, and then we measure the velocity to reconstruct that vortex. Okay, so first I solve this problem with direct numerical simulation to generate the data, and then we try to reconstruct pretending that this data is actually measured. So this is the L curve. The L curve, we have the Sobolev semi-norm of the field versus the misfit here. And we start increasing the parameter that multiplies this, that penalizes this norm, this semi-norm. Okay, so from here to here, we are increasing the epsilon. We begin with epsilon 10 to the minus 8, then 10 to the minus 7, all the way up to 10 to the minus 2. And we want the point that basically minimizes both contributions. So intuitively, the point that minimizes these 2 contributions is the point that is closer to the origin. So this is the point that has the best reconstruction. And in this case, the optimal epsilon was 10 to the minus 3. So this curve usually looks like an L, but since our construction is adaptive, it doesn't look like the classical L, but some sort of L. And this is our reconstruction for a given time. So here we have the numerical simulation. Here we have the reconstruction, and here we have the error. Since we have very sparse measurements, we have a large error at the interface of the 2 fluids. So the fluid here is going left and the fluid here is going right. And we have, at this interface, we have a sharp change in velocity. You can see here a sharp change in magnitude and direction. And that is particularly tough to capture with any sort of approximation, in fact. So we would need a lot of data near this interface to capture these changes. So here we finish the discrete divergence-free projection. In the first paper we published, we also have temporal approximation using singular value decomposition, but since I won't have time, I will jump now to the discrete Hodge-Helmholtz decomposition. So let me go right to the point. So we solve here for an underlying field that I'm not showing. We solve the Hodge-Helmholtz decomposition on this domain 0 to 3 pi cube. Squared, sorry, this is two-dimensional. The residual boundary for both fields is 50%, and the stopping criterion for both fields is 10 to the minus 3. The Sobolev regularization, we use 10 to the minus 4 for both fields and 1.5 for the penalization of the kth gradient. And after 15 iterations, we obtain these two index sets. And here I show you the error of the total field. So here we have the true field minus the sum of our two components, the curve-free and divergence-free. Here we have in this column the L2 error, the L infinity error. Here we have the error in the divergence field and the error in the curve-free. So here should be C, not D. And an interesting thing about working with Fourier type of approximations is that these physics-informed spectral sparse learning is endowed with a spectral convergence. So that means for a constant Q, we have that the coefficients V alpha and the Fourier coefficients var sigma alpha, they go to 0 at an exponential speed. So B here is the exponential index of convergence. And for this problem, the exponential index of convergence is about -20. So that's pretty high. That is a pretty fast convergence. That means that growing our index set will improve brutally the accuracy of our approximation. And here I show why this is a spectral method. And basically we have that the divergence-free component and the curve-free component, they go to 0 pretty quick, the energy of the boundary. And here are the iterations. At every time we increase the boundary of our approximation. At the beginning, we start with basically an energy of 99%, and we have these two reconstructions, which are, this is the error of these two reconstructions, and it's pretty bad, as we can see. As we increase the number of basis function, our reconstruction gets better and better, up to the point that adding more basis function is not beneficial at all. And this happens pretty quick, you know. Here we have 10 iterations. Basically, that means we increased 15 iterations up to here. That means we increased our boundary set 15 times. And if we plot these in a log versus log, we get a straight line because this is the convergence. And we find that beta is about -20. If we compare this convergence with other methods and using the nomenclature of spectral methods, using finite elements, we have algebraic convergence or convergence that is h to some constant, usually related to the degree of the polynomial approximation, and it's similar for neural networks, at least with a single layer. And the convergence here is way faster. So for this first problem, we have here the underlying field we want to decompose. we have access to these measurements, and this field is composed by the sum of these two fields. And our approximation, our Fourier reconstruction, give us these divergence-free and these curve-free fields. They are pretty similar. We have some differences here on the boundaries. As you may see, it's not perfect, but this is because we have limited access to the measurements. And here we have also some issues with the reconstruction, but you cannot see these issues in the field reconstruction. This is because the velocity, the magnitude here are pretty small. And similarly here, they are near zero. And these are the errors. As I said, here we cannot see the error, but actually the error in the total reconstruction is larger than the error in the divergence-free and curve-free field. And here we solve another different problem. I guess I'm running out of time. So in this reconstruction, or in this Helmholtz decomposition, we end up getting these two index sets, this for the divergence-free, this for the curve-free. These are the L2 errors that we get, the L infinity errors, and for this case is below 2.5%. This was the underlying field. We aim to decompose. This is the divergence-free and the curve-free. This is our approximation of the divergence-free and our approximation for the curve-free fields. And this one is pretty decent. I don't see any difference between these two. Here, for the curve-free, we see some differences here close to the boundary. We could fix these using a periodic extension here, because this, of course, this is not periodic. This is a crime. In fact, we should have used, but I wanted to mimic exactly the same domain. And this is the final reconstruction. And again, it's pretty decent. We cannot see any difference. One thing that I didn't mention, for the divergence-free projection, using very few measurements, about 10, we were able to reconstruct this field. However, the Hodge-Helmholtz decomposition is a problem that requires many more measurements to provide us with a decent decomposition. So in this case, I had to use about 200 measurements to perform this decomposition, which is still low. 200 measurements to do this decomposition, it's nothing, but it's much more than what is required for the divergence-free projection. And these are the errors of our reconstruction: the divergence-free, the curve-free, and the final error, which is the sum of the two fields. And to conclude this talk, I will show you a three-dimensional example, and the parameters here are pretty much the same. We end up in this problem with 583 bases for the divergence-free field and 477 bases for the curve-free field. And we end up with these index sets for the divergence-free, for the curve-free. These are the L2 and L infinity errors that we get here. So they are pretty low. They represent less than 2%. Here on the top, we have the divergence-free field, the curve-free field, and the sum of the two. These are the errors we get here. It's the total error, the divergence-free field error, and the curve-free field. And that's all. Thank you very much.
Thank you, Luis, for the nice talk. Let us see if we have questions from the audience. Shihab.
Many thanks, Luis, for the nice talk. Sorry, I'm not expert in this field, but what is the value, I mean, in practice of reconstructing, I mean, these fields and these type of problems. Can you comment on that?
Yes. So, well, the idea is first to construct the tool to solve physics-informed type of problems. And I'm just applying to two particular fields here. One is the divergence-free projection. This is a very common tool. Imagine that people working in experimental fluid mechanics, they use kriging, for instance. They measure the velocity everywhere or everywhere they can, and they reconstruct the velocity. But then the line velocity is divergence-free. When they reconstruct the velocity with kriging, or they interpolate with kriging, they get a field that is not divergence-free. So you are eating the physics there, you are disregarding all the physics when you do this type of interpolation. And the same people working with meteorology, you know, with even with geography, they measure the wind and they just interpolate. And the wind is divergence-free. If you just interpolate, you certainly end up with a field that is not divergence-free. These are two cases. And the Helmholtz decomposition, well, very recently, the Navier-Stokes equations were written in a way that you can solve them using the Helmholtz decomposition. So if we can do that, that would be awesome, because when you rewrite the Navier-Stokes equation using the Helmholtz decomposition, you can get rid of the mass equation for compressible flows, which is a pain in the neck because it's a hyperbolic equation. And you end up just with parabolic equations to solve. So then you have there the other application.
Hello, Luis. It's Andre here. That was a very nice talk.
Sorry.
You had some...
Also, you can use the Helmholtz decomposition to detect hurricane formation and fingerprints for fingerprint analysis. Yeah, sorry, Andre, sorry for interrupting you.
Oh, very nice. I had two questions for you. The first was regarding how do you pick the points where you make observations, if you sample uniformly or something like that. And the second is if it's possible to know how to pick these observations in a way of improving your reconstruction as much as possible.
Yeah, the first one, the first question, how I pick those points, just random. I sample from a uniform, but because the idea is that I have limited access to this and they are fixed. The points, they don't change through the optimization process. Because usually if we have velocity measurements for the wind, the stations are fixed. You cannot change, or I mean, it's not doable. So then we keep fixed the measurements. Okay, now the second question is more like towards solving PDEs, how we can sample these efficiently. Well, if we have no data, what I do, it's pretty useless because you could go for fast Fourier transform. If you have data, then you want to combine data with PDEs. Then the question is, well, how to integrate the data with the PDE optimally, how you sample the data optimally. I don't know, probably using something like a quadrature. Yeah. But if the data is fixed, there is nothing to do, right? I don't know if that answers your question.
Yes, thank you. Yes, okay, sorry. Okay, we have another question from Ben Mansour.
Hi, Lee.
Hi, Ben.
I'm sorry, I
I can't hear you.
It's fine now.
Yeah.
Okay, can you hear me now?
Yes, I can. Now
Okay,
I can.
good. So I was apologizing to miss the first part of the presentation. Somehow I thought that it was like starting at 5. So I think I was referring to the last agenda, to the previous agenda. So thank you. I think this is a very nice presentation. And we are trying to develop something similar by using pins for electromagnetic with application to geoscience. But
Nice.
we are having a big problem, so we cannot make the things converging, but we are mostly interested on frequency domain solution. So my question is the following: what do you think about like applying this approach to get a solution in the frequency domain?
Well, here, I mean, since this is a finite representation, I guess, I mean, it's just the Fourier coefficients, right? You have in your problem, you have data, right? And you want to solve the PDEs with data. Is that right?
Yes, we do have the PDE with the data, but what we start to do is like solving the PDE using pins, but
In
we
the
get some
frequency
problem.
domain.
Yes, and yes, in frequency domain, but we get some problem with the convergence. So we are trying to find a way to you know, to escape to these things. So we are now, since I saw this presentation, I was just thinking the possibility of applying this to the problem. But did you know anything about like this type of approach for frequency domain problem?
No, I don't. But if you work with Fourier series, I mean, that should be straightforward. The problem is that you are working with neural networks, right?
Sorry?
You are working with neural networks.
Yes.
Yeah. Yeah. No, I don't know, honestly. I don't know.
Okay. Thank you.
But you may try to use these sort of tools to see if you can. I mean, these tools may be useful because you also have divergence free and curve free when you solve the Maxwell equations. And here you get that for free, basically. So yeah.
Thank you for the.
We can discuss that if you want.
Sure.
Thank you for the question, Ben.
Okay, more questions? So if not, let us thank again Luis for the nice talk.
Thank you, guys. Nice to see you all.
Yeah, let us have 4 minutes break and then we continue.
We try and get the slides to open. Let's see.